So now we want to do the same thing for SUNs. Okay, so SUNs, the SUN groups, the SUN group, you know, it's fundamental, you know, defining representation are n by n matrices, right? They're complex matrices. Complex matrices that act naturally on Cn, right? So we can say if Q, say, is a n-dimensional, you know, vector in Cn, you know, that would be, we call Q, we should write Q as Qi. Qi is a fundamental representation of SUN. Okay, is this clear? Qi is a column of n numbers. As I've asked last time, we will always we shall always identify the matrices of the representation by n matrices of the representation, you know, with the vectors that they act on. Okay, it's a kind of a that's how you. It's implied when we're talking about the vectors. We are also referring to the matrices. Okay. So when we are saying Qi is the fundamental representation of SUN, we are also saying, making reference to the n by n SUN matrices that act on Qi. Okay? So Qi is what we call an n of SUN. Okay, it's an n-dimensional representation of SUN. Now, there's an interesting fact about SU matrices, and the idea is that if, say, TA are generators of SUN, which means that we have TA, TB, I of F, A, B, C, T of C, then you can show that if you take the complex conjugation of this, then you have TA star, TB star, and then you have minus I, F of A, B, C, TC star. Now you can absorb this minus sign into this guy, and similarly this guy. So you see that minus T star of A are also elements of the Lie algebra. Okay. Now, the idea is that are they equivalent representation? Okay. Are they equivalent representations? Now, two representations are considered equivalent if two representations are equivalent, if there exists a matrix S such that for all the generators of the Lie algebra of, say, SUN, T prime, okay, let's say two representations, say T and T prime, so T and T, so this one set, this is another set, are equivalent. If for all T's, there is a matrix S such that there's a similarity transformation between them. Okay. If that is the case, then the two representations are equivalent, and there is a straightforward transformation between them. But it turns out for SUN, for n greater than 2, so this is not for SU2, it turns out for SUN, the representation with the matrices T star minus T star and T are inequivalent, okay? So SU2 is not large enough for this to be true. There is no wiggle room in SU2, but starting from SU3, these are all, they are not equivalent. Okay. So if I say TA generates some, matrices G, which act on, let me use U rather than G. U, that act on, say, QI, then TA star of minus will generate some matrices U of SUN that will act on a different space, which I'm calling QI upstairs. And you can show that this QI upstairs is the same thing as QI star. It makes sense, right? Because you're going from here to here by complex conjugation. So you should also go from here to here by complex conjugation, right? But we write it like that. Okay, so QI is called the fundamental, right, representation, or N, as we mentioned before. But QI upstairs is called the anti-fundamental. Okay, this is physics language. Representation, or N bar. And the anti comes from the fact that in strong nuclear physics, it turns out that for SU3, the three quarks, up quark, down quark, and the strange quarks are approximately in a 3 representation of SU3. And then the anti-fundamental representation consists of the anti-quark, anti-up quark, anti-down quark, anti-strange quark. Okay, so any questions? Okay, so far I'm just giving out information. So how does QI transform? Well, under QI, it should transform like, it'll go to QI prime. We'll have an SUN matrix acting on QI, right? Where U is an SUN matrix. And then QI upstairs should transform like, QI upstairs should transforms like Q J upstairs, U dagger of JI. Okay, so these are the dagger of these matrices. So we would expect this thing, Q dagger Q, to be invariant, right? Should be a scalar, because that's what unitary matrices do. You know, we defined orthogonal matrices which will keep this object invariant. So that led to the orthogonal group ON, whereas this led to the UN group. So SUN is just a subgroup. So this should be invariant. Let's see if this is the case. So what is Q dagger Q? Well, it's just QI star QI. There's a sum over the repeated index. But we have defined Qi star to be Qi upstairs, and this is Qi downstairs. So under a SUN transformation, the first factor goes to, there's a Qj, U dagger, there's an I here, there's a J here, and this guy goes to U of IK, Q of K. But these guys are just, if I write it out, it's U dagger U equals, and we know that is 1. So we can replace this by Qj delta. The sum is over the I index, so we have K index and a J index left over in the delta, and there we have Q of K. Using the Kronecker delta, I can turn K into J, so we get Q of J, Q of J, which is of course Q dagger Q. So we have established that yes, this is indeed a scalar under SUN.